Here we're going to solve a system of equations using elimination, which really is the most systematic and efficient way to go about it. Here's our system of 3 equations and 3 unknowns. Our first job is to strip away the stuff that doesn't matter when it comes to making decisions about how to solve the system. So I'm making a matrix of just the coefficient values, like so, and maybe I'll put a little line there to remember that there's a separation between the left and right sides of these equations. When we do elimination, whether it's in matrix form or not, every choice we make is based on the numbers. It doesn't matter whether the variables are x, y, and z, or p, d, and q, or whatever they are, so we don't need to see them. And remember that at any step along the way, there's a two-way street between a set of equations and the block of coefficients that shows up in your matrix. And so as we manipulate this matrix, we're also manipulating the equations, stupid pop-ups, and at some point we'll get back to where we can take information from our rearranged matrix and transfer it back over to useful information about the solution to this system. So having converted the system into this matrix, now we forget for a second that we're dealing with a system of equations, and let's just play that elimination game, which, remember, our goal here is to introduce 0, 0, 0, and then 1s down the diagonal, when that's possible. So I see a couple of choices already for this elimination. I'm going to take 7 row 1 minus row 2, and I'm going to dump that where row 2 currently sits. And I'm going to take 2 row 1 plus row 3, and dump that where row 3 currently sits. So row 1 is not getting bothered. We're borrowing it when we multiply it by 7 and 2, but that's just temporary, so we don't need to replace it. So let's do 7 row 1 minus row 2, entry by entry. So 7 of those minus that gives us a 0. 7 of those, so 14, minus the 3. 7 of those, negative 28, minus 5, negative 33. Let me write this a little more clear that that's an 11. I don't want to forget that later on. And then the last entry, 7 of those minus that, so negative 7 minus 26. So we're getting some big numbers, but I can already see how we're going to clean that row up pretty quickly. Now let's do the third row. We're going to operate as 2 row 1 plus row 3. So 2 of those plus that. There's our 0. That was the whole point. 2 of those, 4 plus that. 2 of those, negative 8 plus 7, negative 1. And 2 of those, so negative 2 plus negative 6 gives us negative 8. And if you like that little vertical line separator, go ahead and put it in. This is negative 2. Let's just make that clear. I'm going to go ahead and clean up row 2 by multiplying by 1/11. So we'll have 1, 2, negative 4, negative 1, 0, 1, negative 3, negative 3. That's much better. 0, negative 2, negative 1, negative 8. Our next job is to get a 0 in this spot. So how about we do 2 row 2 plus row 3 and dump that where row 3 currently sits. We don't want to involve row 1 anymore because that will mess up the zeros we've already put in place. Here we go. 2 row 2 plus row 3, 0 and 0. 2 of those plus that, 2 plus negative 2. Down the line, 2 of those, so negative 6 plus negative 1. And 2 of those, so negative 6 plus that, negative 8, which is negative 14. And then I'm going to do 1/7, negative 1/7, row 3 into row 3, just to clean things up. That will give me 1, 2, negative 4, 1. negative 1, 0, 1, negative 3, negative 3, and 0, 0, 1, 2. Yeah, so there's those vertical bars for those of you that like them. Now we're at a decision point here. We're going to exit the elimination process here and go back to our solutions. Remember that at every stage there's a back and forth between the coefficients we see in the table at any stage and the system of equations that's getting carried along in the background. When we first started, we have the full system with all its coefficients put in its matrix form. We've now eliminated a bunch of stuff and turned it into zeros, but we can still take this version and turn it back into equations. For example, row 3 now tells us that 0x plus 0y plus 1z equals 2, or in other words, z equals 2. Row 2 tells us that 0x plus y minus 3z equals negative 3, or it tells us that y minus 3z equals negative 3. But we've already learned that z equals 2, so that means that y minus 3 times 2 equals negative 3, or y minus 6 equals negative 3. Add 6 to both sides, y equals 3. And now we know 2 of our 3 solution values. And then finally, row 1 at this stage of the table tells us that x plus 2y minus 4z equals negative 1. However, with the values of y and z that we have, now we can write x plus 2 times y, so 2 times 3, minus 4 times z, which is 2, equals negative 1. Yeah, I don't need quotes there. X plus 6 minus 8, so how about x minus 2 equals negative 1? And solve that for x. X equals, well, add 2 to both sides, x equals 1. And then I suppose to be good, that thunk you just heard was my dog hitting her head on the underside of the table. That must have hurt. Sorry, dear. I'm guessing there's a little bit of thunder rolling in. She always crawls under the table like that when she gets nervous. So we have x is 1, y is 3, z is 2. And that is the solution set to this system of equations. We should be good and go test these numbers, but I'll let you do that on your own time. I mentioned at this point right here, we were at a decision point. I decided to abandon the elimination and just go right back to the equations. You could stick here and keep going with elimination to put a 0 there, there, and there. And when you're done with that, you have right in front of you x equals its solution, y equals its solution, z equals its solution. That is called reduced row echelon form, but that's for Math 124.